Hello. In this video, we are going to continue our study of infinite sequences and series, and more specifically, I'm going to introduce what I mean by an infinite series. We'll explore a couple of examples and describe how the concept of a series is closely related to the concept of a sequence, and along the way, I'm going to show you something that will, I hope, help you distinguish between these very similar but different concepts, a sequence and a series. So in the last few videos, we've been exploring sequences, and remember that a sequence is a list of numbers in some order. There's a first term, a second term, a third term, and there's just a list of numbers that goes on forever, and we were exploring whether a sequence converges or not, as in, do the terms, the numbers in the list, do those terms approach a specific value? Do they converge and get closer to something? When we talk about an infinite series, like we're doing here, it refers to a sum. It means we're talking about addition. So as opposed to a sequence, which is just a list of a bunch of numbers, infinitely many of them, in some order, an infinite series means, well, let's take something like that, a list, but instead of just writing them with commas in between them, let's add them together. Let's sum or add all of those terms. And here are some examples. Look at the one on the left over here. 1 plus 1 plus 1 plus 1 plus 1 plus, and I hope you see what this rather boring pattern is. That dot, 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 that ellipsis means keep adding plus 1 plus 1 plus 1 forever. Don't deviate from that pattern. Here is that exact same series translated into summation notation. This letter, that symbol right there in the front, that's the Greek capital sigma. That's from the Greek alphabet. That's essentially their capital S, and I hope it's clear why we're using an S. We're talking about a series. We're talking about a sum. It's a reminder that we're going to sum, that we're going to add together a bunch of things. That lowercase n, we're going to call the index of the summation. It refers to the fact that we're going to let n start at 1. That's the bottom there. And it will, by assumption, increase by 1 along the counting numbers. So this means start at n equals 1, and then go to n equals 2, and then 3, and then 4, and then 5, and then so on. And then the number at the top tells us when to stop. And in this case, it says infinity, so that means n is just going to keep increasing by 1 forever. So together, the n equals 1 and the infinity on the top tell me that I'm going to let n equal 1, 2, 3, 4, and then continue forever. That sigma, the capital S, the S stands for sum, so it means I'm going to add together all of the things when n is 1, and when n is 2, and n is 3, and so on, and the things that I'm adding together, the terms, are indicated in this part over here. So that thing to the right of the summation, think of that as a little formula, a little function that says these are the terms that you're going to be summing, that you're going to be adding together. So what this means is plug n equals 1 into that formula, that function that I have in the blue highlight there, and add that to my summation, and then make n equals 2, plug that into the blue thing, and add that as a term to my summation. Then plug n equals 3 into that formula and keep going. Now, this as this first silly example, you'll notice that there's no n in that blue circle. The summation is just 1 all the time, no matter what n is. That's because I'm trying to represent that summation of all ones. The pattern is it never changes, it's constant. So of course it's not too surprising that my formula, my function here, doesn't really literally depend on n, it's just constantly 1. So this set of symbols down here, this sigma, this summation notation, means exactly the same thing as this. It says add 1 plus 1 plus 1 plus 1 plus 1 forever and ever and ever and never stop. Let's look at the example in the middle, the second one, because there I have a function that actually depends on n there. So look how the summation symbol here and the n equals 1 to infinity, that's all the same as before. So this still means make n 1, plug that into the formula, see what you get. What's 1 over 2 to the 1? That's 1/2. Hey, that's the first term in my summation. Plug n equals 2 into this little formula. What's 1 over 2 to the 2? What's 1 over 2 squared? That's 1/4. That's exactly the next term being added in my summation, in my series. Plug n equals 3, I get 1 over 2 cubed, or 1 over 8. That's exactly the third term. And so on. 1 over 2 to the 4th is 1 over 16. That's the fourth term. And then just keep going. And so if I had just written this stuff that I'm circling in blue right there, I'm hoping that you would see the pattern there, that I have powers of 2 in the denominator, that I'm doubling the denominator every time to get from one term to the next. And so you might be able to infer that the next term I mean is 1 over 32, and then plus 1 over 64, and then plus 1 over 128. But this summation notation down here is just more concise. I don't have to write out a bunch of terms and then say plus ... Oh my gosh, I hope my reader understands what I mean and they see the same pattern that I do. Arguably, it's much better and a more effective communication for me to just say, hey, literally, this is the pattern that I mean. I'm not going to leave it to you to guess what it is. I'm going to say, this is the pattern. It's 1 over a power of 2. The example on the right here, the third example, notice that these terms that I'm adding together in this series, they are 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And I know we never usually write 1 as 1 divided by 1 because that feels redundant. But you can think of that number in this way here because you can see how it fits the pattern of all the other terms. It's 1 over 1 divided by a whole number, a counting number. And that's exactly what this summation notation down here says. Start with n equals 1, plug that into the formula, and I get 1 over 1. There's my first term. Then plug the next value, n equals 2, in, and I get the next term. Then plug n equals 3. I get the third term. And keep going and add all of those numbers together. Sum them. Remember, sigma s means sum. So those are just 3 examples, and I've picked them here because we're going to explore the first example to show you that a series can diverge. I'll tell you what that means. And the second example I'm going to use to show you that an infinite series can converge, and I'll tell you what that means. And then I'll come back to the third example in a later video, just because it's a slightly different beast from the others, so to speak. Now, because these are infinite series, we have some interesting situations to deal with, some interesting questions to answer. If I had a finite series, as a simple example there, what if I just said 1 plus 2 plus 3 plus 4? That's a finite series. It's a sum with only 4 finitely many terms. There is the same thing written in summation sigma notation. It says let n go from 1, but then instead of going all the way to infinity like the other examples, let's stop at 4. And what's the formula? What's the pattern? What's the function that I'm plugging n in to generate these 4 terms? Well, each time n goes up by 1, I want the term to go up by 1. So when n is 1, the first term is 1. When n is 2, the second term is 2, and so on. And that adds up to 10. That adds up to a specific finite number, because I'm only adding finitely many things. It has to happen that way. But when I have an infinite series with infinitely many terms, the result could be kind of like that. Believe it or not, if I add up infinitely many things, if those things themselves that I'm adding together, if they get really, really tiny, if they get really close to 0 fast enough, then even if I'm adding infinitely many of them, they could all collectively add up together to something finite. And we're going to see an example of that, the second one up in the middle up there, that's going to be our example. And so that's when we'll say that a series converges, when all of the terms, even though there's infinitely many of them, collectively, if they all add up to a cumulative total that's a finite specific number, we'll say that the series converges. And if it doesn't do something like that, then we'll say it diverges. So the way that we're going to get a handle on that, deciding whether a series converges or diverges, is through this concept called partial sums. And I like to think of a partial sum as meaning I'm partially adding together all of the infinitely many things that I'm supposed to be adding together in my series. So I like to say, imagine I'm adding up an initial chunk. Initial as in from the beginning of the series. I'm going to add up the first 3 or the first 4 or the first 5 or the first 100, and not somewhere from later down the line. I'm always going to start from the beginning, the initial part of the series. And a chunk as in I'm going to add up to a certain point and then stop. I'm not going to think about adding up all of them forever, at least not yet. That's going to come from a limit later. But add up just a chunk of them, the first 3 or 4 or 5 or so on. And so this is going to produce another sequence. And so this is, I think, part of the challenge of learning about sequences and series is they're so closely tied together that even when we talk about a series, there's literally 2 different but closely related sequences happening. So let's use this 1 plus 1 plus 1 plus 1 example as a way to just introduce and define what I mean by partial sum. So imagine I have this infinite series, 1 plus 1 plus 1, forever and ever. I want to generate the sequence of partial sums. Now, when I say 1 plus 1 plus 1 plus 1, that's referring to one sequence off the bat. You can see that there's a sequence of terms, and those are the things that are being added. Those are the things around in between the plus signs. You could think of this as an infinitely long scroll, a list of things that I'm supposed to add together. And on this example, it just so happens that my infinitely long list of paper just has a ton of ones printed on it forever and ever. Now, once I have that list of numbers that I'm supposed to be adding together, I can start writing down on a separate piece of paper a running total, a total of adding up just some of the terms so far. So when I say sequence of partial sums, think of those as the running totals, like the cumulative amounts that I've added up to if I just add up some of the terms so far. So imagine that I just added the first term, just the first one. Well, that's what this s sub 1 equals 1 means. It says if I add together the first one term of the series, I get a total of 1. This means s sub 2, if I sum the first two terms, then I'm adding 1 plus 1, and they add up to 2. This means if I sum together the first three terms of the series, then they all add up to 3. And this means if I sum the first four terms of the series, they all add up to 4. And I specifically picked this example to make this pattern, I hope, abundantly obvious. If I add up the first n, an arbitrary number, whatever number that is, if I add up the first n terms of the series, then I have exactly n ones all added together. So it shouldn't be a huge shocker that they all add up to n. I have n times 1. And when I say, does the series itself, this infinite sum of a bunch of ones, does that approach something? Does that converge or diverge? Well, now we can phrase that question in terms of the convergence or divergence of a sequence. And so this is now when we get to use all of that knowledge we've been building up from the last few videos about sequences. The convergence of this series that we're talking about is 100% tied to, it's totally equivalent to the convergence of that sequence of partial sums, Sn. Asking whether the series itself converges is asking whether that sequence of running totals is converging to something. And in this case, I hope you see that the sequence itself is, that sequence of partial sums is diverging to infinity. And that should kind of match up with what your intuition would be. If I were to start adding ones over and over and over, my running total would just keep going up by 1. It would be 1, and then 2, and then 3, and then 4, and then 5, and it would just never stop. It would just grow and grow and grow all the way to infinity, and that's our conclusion here. This series diverges to infinity. And the reason for that is the sequence of partial sums itself, that's diverging to infinity. Here's a formal definition of sequence of partial sums, and it might help you to pause this video or go back a little bit and look at the example we just did and then look at the formal language in this definition box to see how it's just trying to generalize what we did in that example. It says, take an infinite series, and here the a's that I'm talking about, the a1 plus a2 plus a3 plus a4, that's the sequence of terms of the series, the things being added together. It's the sequence of terms of the series, the things that I'm going to be adding together. So in the last example, that was the sequence 1, 1, 1, 1, etc. Then the sequence of partial sums, which we're going to use Sn to indicate S for sum, and I guess for sequence as well. It's defined as follows. Sorry about that little typo in the first red box there. S1, the first term in the sequence of partial sums, is literally equal to A1, the first term of the series, the first thing being added together. because S1 means sum the first one things, so of course I get that first one thing. S2 means sum together the first two things. S3 means sum together the first three things, and so on and so on. Another thing you might notice that I'll just point out here that may help you when thinking about some other examples is that, for example, S4 is the sum of the first four things, but notice that that's literally equal to the sum of the first three things plus the fourth thing. So a way I can write that down is to say that the fourth partial sum is the prior one, the third partial sum, plus the next coming term in the sequence of things to be added, A4. And so I have that written right here for the observation we just made about S4 and its relationship to S3. That S4 is S3 plus the fourth term, A4. And here is that same fact written down in general for an arbitrary, for any random number n. The nth partial sum comes from adding up the first n minus 1 things and then tacking on the next one, the nth thing to be added together. And here's another way of saying that too using summation notation. This just says the nth partial sum comes from, sorry for that typo there. That should be an n at the top, not an infinity. In general, the sequence Sn is defined by saying the nth partial sum is the summation of all of the a sub whatevers as that whatever goes from 1 to n. In other words, in symbols, this says in words, the nth partial sum means add the first n terms from the sequence of things to be added. Okay, so all of that leads us to define the convergence of an infinite series by recasting it in terms of the convergence of a sequence, which, hey, we already defined a couple of videos ago. We talked about how a sequence converges if the values in the list in the sequence, the terms of it, if those terms are approaching and getting arbitrarily as close as we could want to some specific value. So if the sequence Sn converges to some limit, let's say S, then that's what it means for the infinite series to converge to S. Whereas if that sequence Sn diverges, then we'll say the infinite series diverges. So this is just a way of recasting convergence and divergence of a series into convergence and divergence of a sequence, which we've already started to study a little bit. Okay, so here's something that I find a useful analogy for visualizing and thinking about the relationship between this sequence of terms and the sequence of partial sums of an infinite series. And this is something that I really like to demonstrate out in class face-to-face, but here we are. I'm going to have to try to describe this on audio and video here. Imagine an infinite series corresponding to someone, you can imagine me at the front of the classroom if you'd like, corresponding to someone walking back and forth along a number line and keeping track of where they go. And conceptualize the sequence of terms, the numbers to be added, as a list of step sizes. So in my previous example over here where I said, think of this infinite series, its sequence of terms being all the ones. Imagine I have an infinite scroll that's printed on it 1, and then the next line is a 1, and then the next line is a 1, and so on forever. That's telling me all the numbers I'm going to add. In our new analogy, think of that as saying you got to take a step of size 1, and then you're going to take another step of size 1, and then another step of size 1, and me reading the list along that scroll to tell me how big of a step to take. And then as I'm doing that, let's say I keep track of where I end up after every step. So let's say I start at position 0, and then I start following this sequence of terms telling me how big of a step to take. So I might take my first step of size 1, and I would write down 1, because I have now landed at position 1 after my first step. And then imagine that I go to the next item on my list of step size and it says 1, so I'll take another step of size 1. And now I'm landing at position 2 along the number line, and that's why I'll write down 2 on my sequence of partial sums, a new scroll that I'm writing down. And then the next step size is 1, so I take a jump of size 1, and then I land on position 3. And so on and so on. Every time I look to take a step, I read my sequence of terms, and I take that step of that size, I figure out where I am on the number line, and then I write that down as an item in the sequence of partial sums. So now you can imagine that if I were to actually act this out, me behaving and walking along this number line will cause me to just keep traveling forever to the right. I'll end up at step 9 and then position 10, 11, 12, and I'll just walk right out the room and clear out of town and forever to the edge of the universe and beyond. And that is the sense in which this series diverges. I am not getting closer to some specific point on the number line. I am just traveling all the way across forever. I'm not approaching any specific point. I'm not converging to something. I'm doing the opposite of that. I'm diverging away from all positions. So as you're reading through examples, try to imagine, and I honestly do this, I find it helpful, try to imagine that each infinite series you're facing, a summation, is somebody walking along a number line. And asking whether it converges or not is asking, if I were to follow the step sizes that are laid out in the terms of that series, would I end up walking towards a specific place? Could you stand somewhere and wait a little bit and rest assured that I would eventually just approach and get closer and closer to your spot? If so, great. That's what it means for this sequence of partial sums to converge to that place. It's what it means for the infinite series to converge to that point. And if I'm not doing that, then that means the series diverges. So let's go back to that second example from the first slide to look at an example of an infinite series that does converge to something. So here I'm going to consider the sequence, and I'm just going to use B instead of A because this is the second example we're looking at. I don't have to say the terms are always B or A or whatever. I'm going to consider a sequence defined by 1 over 2 to the n. So this sequence goes like this: a half when n is 1, a fourth when n is 2, an eighth when n is 3, and so on and so on. So remember that this is referring to a sequence of terms to be added. And so really in this example on this slide, I'm trying to address the question that I have written in this outlined black box right here. Does this infinite series converge or not? If I think about summing, adding together all of the Bn numbers, the terms in that sequence, will that add up to something finite or will it not? So what about this series? That's what I've written in summation notation right there. Well, let's look at the partial sums of this series. So when I say S1, that means add the first one term from that series. When I say S2, that means add the first two things from that a sequence of terms. And I can see they add up to 3/4. And when I say S3, that means add up the first three things from that sequence of terms. And when I say S4, that means add up the first four things. And you may want to pause here and check my work and confirm that all these results that I'm getting on the right, the 1/2, the 3/4, the 7/8, the 15/16, that all these things add up to. But as you're doing that, I'll also just point out that remember that relationship we noticed in the definition on one of the previous slides where I said that each partial sum is the one before it plus a new term. And you can kind of see that happening here where, for example, S4 at the bottom is the previous partial sum, S3, plus a new thing. And so that's why I've labeled, I've not done any new work, essentially, to say when I do a half plus a fourth plus an eighth, by gosh, I already know that adds up to 7/8. I'm not going to do that calculation again. I'm just going to tack on the new 1/16 to calculate that new total. But I'm hoping you'll notice a pattern from these results. The 1/2, the 3/4, the 7/8, the 15/16, that's all a power of 2 minus 1 divided by a power of 2. Right? 16 is a power of 2 and 15 is 1 less than that. 8 is a power of 2 and 7 is 1 less than that. That's the pattern that I see. And so that's why I'm able to write down this pattern that I've seen from the partial sums, their totals. Now, for the technical listeners, I would do some induction argument to verify that that's happening. For now, it's fine for me and my students to just say, hey, look, that seems to be the pattern. I believe that it keeps going. And now the question that we're really trying to address, does this series converge? If I added up all those numbers forever and ever and ever, will that add up to something? Well, now we've recast this as a sequence question. Does this sequence converge or not? And now think about employing some of the techniques that we've been talking about in the last few videos. As n grows to infinity, in the numerator here I see 2 to the n going to infinity. Minus 1 doesn't change it a whole lot. And 2 to the n in the bottom, that's also going to infinity. And before you pull out your L'Hopital's rule tool from the toolbox, think of it this way. When n is a huge number, 2 to the n minus 1 is effectively the same number as 2 to the n. If I take a billion and I subtract 1, it doesn't change it a whole lot. If I divide by a billion, then I have effectively a fraction that's really, really close to 1. And as n gets bigger and bigger and bigger, as I take this limit, that ratio gets even closer and closer to 1. So in fact, yeah, this sequence really does add up to 1 in a very real sense. This series converges to 1. If I were able to somehow literally add all infinitely many of these numbers, a 32nd, a 64th, a 128th, blah, 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 forever and ever and ever and ever, they would all add up to an equal 1. And since we're on the topic of this example, let me jump in with a little geometric visual argument in here, just to hopefully maybe convince some of you that are still skeptical about infinitely many things adding up to a small finite number like 1. Let's think of it this way. I'm going to draw a square of size 1 by 1, so this total area of the square is 1, right? Now, let me start dividing the area into pieces. What if I draw this vertical line straight through the middle here? So that's an area of 1/2. And then what if I take the rectangle on the right over here, and I cut that in half? Doesn't this area right here equal 1/4? Because I have half of a half of the original square's area, which was 1? Yeah. Then let's look in the top right corner there. That's also 1/4 because it's the same area as the region that I just shaded underneath. Those are the same. So that's also a quarter. And so if I cut that thing in half and I look at that area, isn't that 1/8? Because it's half of a quarter? Maybe you see where I'm going with this. Let's take that corner in the top right now, that rectangle, and cut that in half. There's a 16th. There's a 32nd. There's a 64th. There's a 128th. And I could keep zooming in, but I'm not going to subject you to that. But essentially, I could keep dividing this in half forever and ever and ever and ever. And I would be showing that if I start adding up these areas, the 1/2 from this thing, and then the 1/4 area from this part, and then the 1/8 area from that part, and then the 1/16th, and then the 1/3, and so on and so on and so on. If I add up all of those areas, can I rearrange all of those rectangles and squares into the area of the whole big square, which was area 1? That's what I mean when I say that this sum, if I were to add forever, it really does equal 1. It is approaching 1 in the sense that if I add more terms from this series, the running total becomes closer to 1. But it equals 1 in the sense that if I could add all of them forever, it really would add up to exactly 1. And if you're still feeling a little skeptical about this, it's kind of the same idea of this limit, where we say that as x goes to infinity, 1/x converges to 0. So this limit equals 0. Not in the sense that I could plug in a specific number to make 1/x output exactly 0, but rather I can make 1/x get really close to 0 by making x bigger and bigger and bigger. So I'm going to erase that now because it's not exactly related to it's not the same idea as the infinite series up at the top, and I don't want anybody reading these notes later to get the wrong notion, but I wanted to say it to you now as you're listening to say, convergence is kind of a weird idea, and I acknowledge that because we're talking about something getting arbitrarily close, but never getting there, but then we still say that it equals. So maybe this discussion here will help you grab hold of that concept somehow. So here's a practice problem, and I will leave the video here for you to read it. Essentially do what we just did in this last example where I gave an infinite series and we started to explore the partial sums looking for patterns, and then eventually took a limit to see what we could conclude about the infinite series itself. I'm asking you to do the same thing here, and hopefully you see the pattern. I have a tenth, and then a hundredth, and then a thousandth, and then a 10,000th, and so on. So just imagine that all these terms are 1 over powers of 10. You know what? I'll even help you out by writing out the summation notation for this. Infinite series there. It's 1/10 to the n, because when n is 1, I get 1 over 10 to the 1. When n is 2, I get 1 over 10 squared. When n is 3, I get 1 over 10 cubed. And so on and so on. So I will let you pause here to work on this. And then here are the solutions to that. I will pause here to let you read this information and compare it to your work, and you can send me any questions or issues or comments that you have with this. And just before I let you go, I want to jump over and show you one thing related to this issue that I've mentioned about the difficulty in understanding how an infinite series has two related sequences going on, the sequence of terms and the sequence of partial sums. So I want to show you something that I think is helpful in thinking about that. So there's a website called Stack Exchange that's a Q&A site with all sorts of subtopics. There's one for math educators, and here's an interesting question on there. How can I teach my students the difference between a sequence and a series? Sequences and series are related concepts, but they differ extremely from one another. Well, I don't know about extremely, but whatever. They're different. I feel that students in integral calculus, Calc 2, frequently mix them up. I find that as well. Part of the problem is that, 1, sequences are usually taught only briefly before moving on to series. Sorry, but that's kind of what we're doing too. Yeah, we use sequences to start to understand series. So we kind of introduce them quickly and then start applying them to series. That's just kind of how it goes. 2, the definition of a series involves two related sequences, the terms and the partial sums. Yeah, that's what we were just talking about. 3, both have operations that take in a sequence and output a number. So when I have a sequence, I might output the limit of that sequence. That's a number. Or if I take in a infinite series, I'm inputting the sequence of terms and I'm outputting a number which is the sum of the series. Like that example we were just doing, the 1/2 plus a 4th plus an 1/8, the output, the sum of that series was 1. And number 4, both of them have convergence tests. You know, like we use the squeeze theorem. That's a way to analyze sequences. Sometime later, we're going to learn a bunch of quote-unquote tests for whether a series converges or not. So that's another point of confusion. What methods can I use to teach students to distinguish between sequences and series? Well, one of the top voted answers down there says, I have no evidence to back this up, nor do I know how I could obtain such a thing, but I strongly believe this is a vocabulary issue, and I would like to see the term series phased out of usage. Oh, wow, interesting. To many minds, sequence and series convey the same thing, a list of items. In modern parlance, we may speak of a television series, which is really a sequence of episodes, or a comic book series, which is a sequence of issues, or the World Series, which is a sequence of games, somewhere between 4 and 7, because it's a best out of 7. And dictionary definitions for series cite everything but the mathematical definition, and you even use all sorts of other math terms like number and set. So if you click on that link for dictionary definitions, it says, a series is a group or a number of related or similar things arranged or occurring in temporal, spatial, or other order or succession. And that's a sequence. So in other words, this is saying that this dictionary treats series and sequence as literally synonymous, that you can swap one for the other. And what I'm trying to say in our math course right now is you can't do that. They're two completely different things. So no wonder you're confused. I am on your side. This is an annoying thing. Later things say set. That's another math word, number, and group. These all have different meanings in math than they do in colloquial language. So let's go back to that answer. What does it say? I'm going to stop using this term. Oh, sorry. Only in math does series mean sum of terms. And the dictionary didn't even capture that definition. When we talk about in Calculus 2, a series, we mean a sum, an infinite summation. But nowhere else does it mean that. I'm going to stop using this term and instead refer to them as infinite sums. It's exactly what they are and immediately triggers the fact that the terms are added as opposed to being listed. Remember, so a sequence is a list, but a series is a summation being added. I don't know whether this will solve the problem of students misunderstanding the differences between an infinite sum and its sequence of partial sums, but I know this can't possibly hurt. Well, as it turns out, some of the comments back and forth in response to that answer got into issues of how in mathematics we have occasionally, and here's an example, we have terms that mean something very specific in math, but they mean different things in colloquial language. And you know what? That's just okay. That's just a part of learning mathematics. Part of the interest of learning math is that you need to know that series for us in our context means an infinite sum, adding a bunch of terms together. But when you go out in the quote unquote real world and you talk about a television series, everybody knows you probably kind of mean sequence. And that's okay. That word means two different things in two different contexts. And all sorts of words have that property. This isn't a problem inherent to math. So although this seems to be contributing to the difficulty of the issue, the word series and sequence, they're so entrenched in the mathematical literature and textbooks and writings that at this point it's almost impossible to change that. So I've decided that we're just going to have to get used to that. So you see the addendum down here at this answer. As the comments below describe, it surely is important for students to recognize that a term like series may have a specific meaning in the context of math that differs from its meaning in more colloquial contexts. So I do not actually exclusively use the term infinite sums and avoid saying infinite series. Instead, when this topic first arises in a calculus course, I show this very post to my students. And here's where I get to say, you know what, guys, that was me. That was me giving this answer. I wrote it, I think it was like 5 or 6 years ago, back in 2014. And at the time, I was also teaching Calculus 2, and I was having this exact same problem. I was struggling to explain to students that a series means a summation and a sequence means a list. And despite me saying that over and over in class, somehow that idea was not sticking well. And at the time, I felt, you know what, I empathize with the students. I understand why it's challenging to sort apart those two concepts because they're so closely related to each other, and because linguistically the words sequence and series, they're so close to each other. So no wonder students are confused. But these comments on the question that I'll let you read on your own essentially convinced me that, you know what, I'm not going to be able to personally change these words, so I'm not going to try to. And I'm hoping this can be one lesson, which is in math, words mean very specific things, and part of learning math is learning that language. And from now on, I hope you know that when we say series, we mean an infinite sum of terms. Those terms that I'm adding together, they follow a sequence. And that leads to another sequence of partial sums, the running totals of adding together those terms. And combined, all of those things contribute to the concept of a series. And you just have to know that those are different but related. So I'm going to jump back to that final example of a practice problem to make sure that you have a chance to see this and attempt it. And then here I'll end on the slide with the answers. I hope you found that last discussion about etymology helpful, and I apologize if it felt a little ranty or tangential at some point. It is something that I hope you can enjoy and learn something from.